Hello friends, welcome back to my channel Medicine Up on Zero. And today we'll talk about the basic of ECG or EKG, whatever you can see over here, the electrocardiogram or electrocardiogram over here. Okay, so the same thing. In German language you just call it as EKG. In normal language in English you just call it as ECG. Okay, so whenever we're starting the topic, the basic of ECG, as we know that whatever the electrical activities that will be conducted where within the heart, that will be expressed in terms of the graph paper, where we'll get in terms of the ECG. Okay. Now, whatever the electrical activities we will get at the cellular level, in the myocardium level, at first let's know about that thing, then we will go into details. Okay. So I'm just taking a hypothetical myocardial cells, for example, from here. Okay. So as we know, I'm just taking 3 myocardial cells. Okay. First. So these are the myocardial cells over here. Okay. So as we know, there will be the productions of the action potential that will be originated at the AC node. From the AC node, it will be raised, or it will be spreaded over the atrium. Then it will reach to the AV node. Then from here, it will reach to where within the bundle of fish. Then Purkinje fiber. Then ventricular myocardial cell. Now, see, in these cases, as I already explained to you before, that whenever there is no electrical stimulation, at that time, these cells will have what the resting membrane potentials. And under the resting conditions, whenever we see there is no activity, there is no stimulus, at that time these cells will have what the resting membrane potential. Okay. I'm just taking the resting membrane potentials for these cells, minus 90 millivolt. So is the resting, okay, let me show over here. So the resting membrane potentials around minus 90 millivolt. Okay. Now there is no electrical activities on the heart. Now for whatever the reasons, whenever we'll get the stimulus on these cells, whenever, for example, I'm showing with this color, we are getting the stimulations within these cells. But whenever the stimulus that will come, as a result we will see the influx of some cations. We can see in terms of the sodium, we can see in terms of the calcium. In these times we will see the influx of cation. You can see in terms of the sodium, or you can see in terms of calcium. Whenever the influx of the cation, so we will get over here this cation that will neutralize the resting membrane potentials, because the resting membrane potential that is negatively polarized, we are getting how much? Minus 90 millivolt. Whenever we are getting the influx of the sodium or the calcium over here, these cations, whenever they will reach within the cells, they will just try to neutralize the resting membrane potentials. For example, they will neutralize the resting membrane potentials from minus 90 millivolt to minus 70 millivolt. Minus 70 millivolt. Okay. This is known as threshold potential. Now, whenever we will see these cells will just achieve the threshold potentials at the on the membrane, the voltage sensitive sodium channels that will be opened, or you can say the voltage gated sodium channels that will be opened. So at first we had the resting membrane potentials. Whenever the stimulus came over here, they just took the resting membrane potentials up to the threshold potentials. So whenever the cells will just achieve the threshold potential, time the membrane that will be activated. Now in these cases we will see within the membrane the voltage sensitive or the voltage gated or voltage sensitive sodium channel. Okay, so whenever it will be open, we will get the influx of the sodium. As a result, we will get the threshold potential that will be more what neutralized from the minus 70 millivolt. For example, we are getting minus 50, minus 40, 0, or ultimately we are getting, for example, the plus 10 millivolt up to here. Now let me see what are the things we are getting over here. We can say we are getting the depolarizations of the cells. So up to now, this is known as what? Depolarization. Now the maximum potentials difference we are getting from here, minus 90 millivolt, 10 millivolt, for example. Okay. After that, whatever the thing we'll see, Whenever it will reach to the peak level, after that we'll see the opening of, at first we'll get the opening of the potassium channel. Opening of potassium channel. So for example, I'm showing the potassium channels with this one color. As a result, we'll see, the potential that will be drop a little bit. For example, up to this much. Okay, let me show. Okay. Now after that, in the same time, we'll see also simultaneously we'll see that whenever the potassium efflux is we are getting over here, at the same time we will also see the voltage sensitive calcium channel that will be also activated, and we'll get the influx of the calcium. We'll get influx of the calcium. So in these cases we are getting the influx of the potassium, along with that we are getting the influx of the calcium. That for a short period we will get what? For a short period we will get, there will be no net change in the potential difference. Try to understand what I am saying, guys. That the potassium that is going out, or we are getting the influx of the potassium, in the same time we are getting that influx of the calcium over here. So in a nutshell we can say there will be no change in the net potential. There will be the net potential of the what? This plus 10 millivolt, or we can say the slightly change from here plus 10 to, for example, I'm just taking 0. Now there will be no net change. I'm just showing with a different color for you. Okay. Now in these phases we are not getting any kind of, in these phases we are not getting any kind of the changes in the potential difference. That's why this phase is known as plateau phase. This phase is known as plateau phase. Plateau phase. Okay. After that we will see, after certain time we will see the calcium channel that will be blocked. After some times we will see the calcium channel that will be blocked, but still we will see the potassium that will start what? That will keep on influx, that will keep on what? Throwing out the potassium. So in this case, after some times we will see this calcium channel that will be blocked, but we will see the potassium channel still it will be active, and it will keep on throwing out the potassium. As we know that we can consider the cells as a bag of potassium. So within the cell, the concentrations of, we can say the intercellular potassium concentration that will be more. As a result, we will get the potassium efflux in the cell. The concentration of the calcium outside the cell is more, within the cell is less. So as a result, we will get the influx of the calcium. Now, whenever the calcium channels that is stopped working, and along with that, we are seeing that the potassium that keep on throwing out the potassium from the cells to outside the cells. As a result, we will get the polarizations, whatever you are getting over here, this plateau phase, that will come down, and we will get the repolarizations of the cell. We will get the repolarization of the cell. Again, it will be at the resting membrane potential. Again, it will just reach to the resting membrane potential. So, what did I say you up to now? See, for example, it's the myocardial cell. These myocardial cells on the proper stimulation. On proper stimulation, at first we are getting the depolarization, followed by repolarization. So these two activities, whenever we are getting that depolarizations along with the repolarizations, and that will just that will go through the whole membranes. So these two things are the two phenomena. Along with that, we just can say what the action potential. So whenever we are getting the phenomenon of depolarizations along with the repolarizations, these two things collectively known as action potential. So you can write it over here. We'll get the action potential. Now these are the things we will get in each cells within the heart. Okay. Now as I said you that I have just taken the adjacent myocardial cells. As we know, within the myocardial cells, in between the myocardial cells, there is the electrical gap junction. There is the electrical gap junctions, right? So whenever the sodium is coming over here on the proper stimulations, so some amount of the sodium, some of the cations we can say, rather we should say over here the sodium that will reach the adjacent cells. Now again, whenever the sodium that will reach over here, that will take the resting membrane potential up to the threshold potential, then it will reach again to the maximum peak level. Whenever it is reaching up to the threshold potential, at the time again the voltage channel or the voltage gated sodium channel that will be opened, and it will take the threshold potentials at maximum peak level. After that, we will see opening of the potassium channel. As a result, we will get the slight deflections over here. After that, again we will see the potassium influx and the calcium influx. So there will be no net change. So we can write it over here, the plateau phase. After that, we will see the calcium that will stop working the calcium channel. Still, the potassium that will keep on throwing out the potassium from the cells outside of the cell. Again, we will get the repolarization. In the same way, we will see also over here the next adjacent cells that will also take some cations from the neighbor cells over here. We can say so some amount of the again the sodium that will reach over here. Again, it will take the resting membrane potentials of the cells up to the threshold potential. It's a normal thing. Okay, once you can understand for the one cell, the rest of the cells you can understand, because whatever the things we are seeing over here in the first cell, so the same type of the thing we'll see in the subsequent cells also over here. Again, threshold potentials. Again, we'll get maximum peak level. Then again, you get the slight or repolarizations for the efflux of the potassium. Then we'll get the plate phase. Again, we'll get the or repolarizations. Again, it will be continuing. Okay. So this is the phenomenon how we are getting the how we are getting the productions of the action potentials through the whole heart. We can say from the SN node it will reach to the AV node, and from the AV node it will reach to the bundle of it. Then the Purkinje fiber. But one thing you need to know that the SN node and the AV node, SN node. Okay, I'm writing it over here. SA plus AV node. So SA plus AV node depolarization takes place by influx of calcium, not sodium. Influx of calcium. Try to understand. Don't get confused. In this case, see, I have said that I just took the normal hypothetical myocardial cells. So in these cases, I have said you that in these cases we will get the influx of the sodium that will take the threshold potentials to the maximum peak level, up to maximum peak level. But in this cases, the SN node over here and the AV node over here, in these cases we will get the depolarization phenomenon that will be taking place by the influx of the calcium, not sodium. Okay, just keep it in mind. Okay, now we don't know how can we just represent whatever the electrical activities we are within the heart in terms of the ECG paper. For that thing, I'm just taking the hypothetical cells from the ventricle. For example, I'm just cells over here, okay? And we just apply the galvanometer and we'll measure the potential difference in the heart, and we'll try to we'll try to present or we'll try to express the electrical activities on the ECG paper. Okay. So for that thing, I'm just taking these cells over here. Okay, let's take. I'm just showing this thing over here. Okay. Okay. See, in these cases, I'm just taking the piece of the myocardium from the ventricle, and we'll see what type of the electrical activities we are getting over here. Okay. As we know, in these cases, we will get the multiple adjacent cells, right? Multiple adjacent. Over here, we will get, and we will get the presence of the electrical window or electrical gap junction in between the adjacent cells. Okay. Now see, and we'll just represent the galvanometer over here. We'll represent the galvanometer over. Okay. Is the needle, and is the positive deflection, is the negative deflection. Okay. Now see, whenever there is no proper stimulation, there is no stimulations or no activations of the myocardial cells at that time, we will not get any kind of the electrical activities within the heart. As a result, whenever there is no stimulation, okay, let me show over here. The first case, no stimulation. Whenever there is no stimulation, it is absent over here. There will be no deflections of the needles. For example, in the needles, as we know, the two sides over here, one is the positive sides and the negative sides. I'm just considering this is the positive, this is the negative. Okay. And it will be bound along with these structures. The positive is the negative side, which is electrodes. In these cases, whenever there is, because this positive and the negative electrodes, or you can say, I already explained you in terms of the bipolar limb leads. You can watch it over there to have a clear concept regarding this topic. Now, whenever we are applying the leads over here, but we are not getting any kind of the electrical activities within the heart, with all the cells are under the resting membrane potentials. We are getting the resting membrane potential with each cells within the myocardium over here. Okay. So as a result, we will not get any kind of the electrical activities within the myocardium. As a result, there will be no proper deflections of the needle. So it will be still in the zero positions. Is the zero, for example, is the plus 10, the plus 20, the minus 10, the minus 20. Okay. Yes, we will not get any kind of the water deflections over here. But in the next case, I will show you over here. Whenever we are just applying the stimulations over here, whatever things or changes we will get, that's the main thing to understand over here, guys. So, okay, let me show the next number 2 case. In these cases, I'm just taking the same type of the myocardial cells or the piece of the myocardium. Okay. Now, these are the group of the cells in the myocardium. They are having the electrical window or gap junctions, by which some amount of the cations, or you can say the sodium in this case, I already explained you, that will be passed from the neighboring cells to the subsequent cells. Okay, now see. In these cases, as I said, we'll just take the galvanometer over here. Okay, the galvanometer. I'm taking the positive side over here, the negative side over here. It's attached to the negative side in these cases, it is attached to the positive side. Okay. Now, for example, in these cases, we are just giving the stimulus within the piece of the myocardium. Now, whenever we are seeing that the proper stimulations, whenever we are getting the proper stimulations, it's coming over definitely on the proper stimulations. I have already explained in the first part of the video that in these cases, we will just do the influx. We will see the influx of the some amount of the cations. We will get some influx of some amount of the cations. For example, we are getting the sodium influx over here. As a result, we will see these cells that will be depolarized. These cells will be depolarized. Now, whenever we will get the productions of the depolarizations over here, try to understand. Whenever we are under the stimulations, we are getting the influx of the cations within the piece of the myocardium. As a result, we will see these cells that will be depolarized. So depolarized means we will get the the movement of the positives. Try to understand, whenever the influx we are getting over here, these cells are converted into we are getting the depolarizations within the cells. That means the cells, it was at first the resting membrane potentials. Right now, the resting membrane potential that will be neutralized by the what? Influx of the. Now, in these cases, we are getting the movement of positive charge. Movement of positive charges. So, whenever we, as we know from the physics, that whenever we get the movement of the charges, as a result, we can see the of the electromagnetic force. So, whenever we are getting the movement of the positive charges over here, so as a result, we will get the production of electromagnetic force, right? Electromagnetic force. Now we can represent the electromagnetic force in terms of the vectors. So for that thing, we'll just draw a vector, for example, in this way. Okay. Vectors. Now try to understand from this figure that whenever we are getting the positive charges, see the positive charges, they are going towards the positive, that the positive charges, so if we see the movement of the positive charges towards the positive electrodes. So whenever we get the movement of the, try to understand in terms of the galvanometer's rules, as we know, whenever the positive charges, or you can say the flow of the positive charges, that will be towards the positive electrode. As a result, we will get the positive deflections within the galvanometer. I am repeating once again. Whenever we get the movement of the positive charges toward the positive electrode, as a result, we will get the movement within the galvanometer within the positive deflections. That means if we just over here, okay, let's draw the galvanometer. Okay, I am drawing the galvanometer over here, guys. Okay, it's the 0, it's the positive 10, for example, it's the positive 20, it's the negative 10, it's the negative 20. Now try to understand, in these cases, as I said, the positive will get, okay, let me show over here, the vectors, will get the vectors, right? We will get the vectors towards the positive sides. Okay. As a result, we will get the positive deflections. We will get the positive deflection. Okay, we will get the positive deflections, and for that thing, we will get a productions of the vectors. In the vectors that will have the positive signs, because the positive charges are moving towards the positive electrons. That's why the signs for the vector that is supposed to be positive. And whenever the positive vectors, or we can say the positive charges are moving towards the positive electrode, as a result we will get the positive deflections within the galvanometer. Okay, and the next case, whatever the thing we'll get, whatever the changes we'll get in the next case, let's talk about that thing. Okay, now see, another important thing, whenever we are getting the depolarizations within the cells, at a time we will get all the cells, whatever the cells are present within the piece of the myocardium, all of the cells will be depolarized. So whenever all of these cells will be depolarized, whenever we will see the complete depolarization, whenever we will get the complete depolarization, after that we will see starting of the repolarizations, starting of or repolarization. So whenever we will get the complete depolarizations, after that definitely there will be no vectors. So whenever whenever we will get the complete depolarizations over here, rather we can say the starting of the repolarizations, definitely from this figure try to understand these positive reflections that will again come towards back to the zero. That means it will it will again reach to the resting membrane potential. That means the complete depolarizations, then we will get the starting of the repolarizations. That means whatever the positive deflections we got for the purpose of the complete depolarizations, after that we will get again the needle that comes back to the normal position, zero. Okay, now let's talk another type of the cells. For example, in these cases we will get now the repolarizations. So whenever we will get the repolarizations, try to understand. Here I am taking the piece of the same piece of the myocardium I am taking over here. Okay. Now in these cases, I have already explained you. We got the complete depolarizations. Right now we have to think about the repolarizations. Right now we have to think about the repolarization. Okay, now see. In these cases, we can represent the cells with a negative sign. The negative sign. And some of the cells I am representing with the positive sign. That means we are getting the starting of the repolarizations from this ending. Is the negative end, is the positive end. Is the negative end, is the positive end over here. Now see, whenever the negative flow, we are getting the negative charge flow over here. So towards the negative electrodes, we are getting the negative charge flow towards the negative electrodes. In these cases, for the same rule, we will get it's the positive sign, is the negative one. For the same rule, if we apply over here, that means what? Try to understand the vectors, the positive vector in these cases we will also get the positive vectors, because for the charge flow over here. In these cases we are getting the positive vector that is going to away from the positive electrodes. So whenever we are seeing over here the positive vector that is going towards the negative sides, whenever we are getting the positive vectors over here, we can say the positive charges that is getting neutralized totally over here. After that we are getting the vector that is going towards the negative sides. So positive vector whenever it will just go towards the negative electrode. In this case, the positive is going towards the negative. That's why we'll get the negative deflections within the galvanometer. We'll get the negative deflection within the galvanometer. Over here, the galvanometer in these cases. Okay. Is the positive side, is the negative side. So in these cases, we'll get the negative deflection. In these cases, we'll get the negative deflection. Okay. Now we'll talk about we'll get the the velocity. We'll get the different kinds of the velocity in the different parts of the heart as far as the ionic movements is concerned over here. For example, if I say over here within the ventricular myocardial cells, we'll get the first velocity. Within the, if we say within the atrium, we'll get the moderate velocity. Within the AV node, we'll get the what? The mild velocity or the less velocity with comparisons to the ventricular myocardial cells and the atrial myocardial cells. So why we'll get this kind of the differences over there? We need to know the mechanisms and the regions over here. Okay, let's talk about those things. Now, before that, if I say over here, if I just make that double thickening, if we take the double thickened, if we just take the double thickened layers over here for the myocardium, try to understand what I am saying you guys. If I take the thickened myocardium, if I take the thickened myocardium, what are the changes we will get over here? As far as the, okay, let's talk these things over here, guys. Okay. Now, so whenever I am taking the thickened myocardium, what is the thickness over here? That is doubled. The thickness we are getting over two times. We are getting the thickness over here 2 times than this one. So whenever thickness over, definitely the number of the cells will be more over here. This is a very basic, simple concept. Whenever we are taking the thickened myocardial piece, simply with comparison to this myocardial piece, definitely try to understand within these things we'll get the more amount of the myocardial cells. So whenever we'll get the more amount of the myocardial cells, whenever we're getting the more amount of the myocardial cells, definitely more amount of the sodium influx will get over here. More amount of the sodium influx, so more amount of the depolarizations. So rather we can say over here, we'll get in these cases the stronger depolarizations. We'll get the stronger depolarizations, right? In these cases, we'll get the stronger depolarizations, and the length of the vector that will be also increased. So we can just come to the conclusions for it, that if we take the thickened myocardium, in these cases the number of the cells will be more. So whenever the number of the cells will be more, the more amount of the sodiums will reach over here. So whenever the more amount of the sodiums will get over here, definitely more amount of the depolarization. So rather we can say we'll get the stronger depolarization. So whenever we get a stronger depolarization, in these cases, the length of the vector that will be also increased. So in these cases we can write that the length of the vector proportionate to length of vector proportionate to depolarization intensity. Okay, depolarization intensity. If we get the stronger depolarization, the length of the vector that will be increased. If we get the the weaker depolarizations, for example, if we just talk about in this case, I'll talk in details later in the second part. Whenever I'll just explain about the evinodal depolarization, in this cases we'll get the weaker, or we'll get the weak depolarizations. As a result, we'll get the vector that will be what? Small over here. But if we talk about over here in terms of the ventricular myocardial cells, in these cases we'll get the stronger depolarizations. As a result, we'll get the length of the vector that will be also increased. Okay. Now, why we'll get this type of difference? Let's talk about that thing. For that thing, at first I'll talk about the cell that is present, the myocardial cells that is present over within the atrium. Then I'll talk about the cells that is present within the myocardial cells within the ventricle. These are different kinds of the differences in terms of the velocity. Okay. For the thing, I'll just take this place over here, then I think it will be easier for you to understand. See, whenever we are just talking about the atrial cells, atrial myocardial cells, whatever the arrangement we will get in these cells, within this myocardium, and we can say within the atrial myocardium. First, I am talking about the atrium, then I'll talk about the ventricle. Okay. Now see, when you are talking in terms of the atrium, I'm just taking the piece of the atrial, atrial myocardial cells over here, and we'll try to compare and contrast with ventricular myocardial cells. Is the atrial myocardial cell? Okay. Here we'll also get the cells. We'll get the cells over here. The atrial myocardial cells. Now see, in these cases, whatever thing we'll get, that whenever the stimulus that will reach over here, that means the cation will get the influx of the cation, within the atrial myocardial cells will get the depolarizations, and in these cases we'll get the much more number of the cells. So whenever the wave of the depolarizations, try to understand guys, whenever the wave of the depolarizations that is supposed to cross this much whole things over here, as a result we'll get the more resistance. Why we'll get more resistance? Because from all cell membrane to the next cell membrane, they can subsequent cell membranes. That means the wave of the depolarization that is supposed to cross all the cell membranes over here, and in these cases we'll get the number of cells that will be higher. Along whenever the number of the cells will be more, definitely try to understand in these cases the radius of the cell that is also smaller. So whenever the number of the cells within the atrial myocardium, let's try to understand from here, within the atrial myocardium number of the cells is more, along with that we will get the radius of the myocardium that will also more over here. Okay, so as a result we will see over here the wave of the depolarizations that is facing more resistance. So whenever we get the more resistance over here, definitely for that thing, the wave of the depolarizations that will have the moderate velocity. We'll get the mild to moderate velocity. But what about these things in terms of the ventricular myocardial cells? I'll take the same thickness about same thickness the ventricular myocardial cell, the piece of the myocardium. What is the differences over here? That's the main thing to understand. Now see, in this case we will also get the myocardial cells. But what's the difference over here? Is the myocardial cells. But within the ventricular myocardial cells, we'll get the presence of one kind of specialized cell that is known as what? Purkinje cells. What is the Purkinje cells? Now these Purkinje cells, what? See, these Purkinje cells, they are what? Large enough. Whenever they are large enough, definitely their diameter that will be also what? More. Whenever the diameter is more, the size is also large. And along with that, in these cells, in the ventricular myocardial cells, especially in terms of the Purkinje cells over here, we'll get the diameter that will be more. That's the first thing. Size is more. And the third thing is over here. There's the presence of more gap junctions. So whenever we'll get the presence of more gap junctions, try to understand these cells. It will be easier for these cells to send the cations to the subsequent cells. So whenever the number of the gap junctions or the electrical windows will be more over here, it will be easier for these cells to send the electrical impulse, or rather we can say the cations, to the subsequent cells very fast. But in these cases, within the atrial myocardial cells, or if we just talk about the evinodal myocardial cells over here, in these cases, what are the thing we'll get? There is the presence of more amount of the cells. So whenever we will get number of the cells, that will be more. Along with that, we are getting the radius of the cell that is also reduced. So whenever the radius of the cells that is also smaller, we can say over here, and the number of the cells is more. As a result, we can say over here the wave of the depolarizations that is facing more resistance. So whenever the wave of depolarization that is facing more resistance, definitely the velocity of the depolarizations, or we can say the wave of the depolarizations velocity, that will be less. That will be mild to moderate. But in these cases, the diameter is more. Within the Purkinje cells over here, we can say the bundle of Fischer, rather we can say over here the ventricular myocardial cells. In these cases, the diameter is more. Whenever the size is more, try to understand, whenever the size is more, definitely the diameter will be more. So along with that, we will get the presence of the more gap junctions. So all these things help the piece of the myocardium within the ventricle to pass the electrical impulse from one cells to the subsequent cells very fast. That's why we will get the faster velocity within the ventricle as far as the electrical depolarization is concerned. And that's why we will get the less, or we can say the mild to moderate velocity within the atrium. Okay, so this was all about the first part in terms of the ECG and the EKG, and the next part we'll represent these things in the graph. Okay, we'll talk about why we're getting the why we're getting the mechanisms, especially why we're getting the QRS complex, why we're getting the T-wave, and what is the PR interval. Okay, the RR interval, And history segment, we'll talk about all these things. First, we'll talk about the physiological things. Then we'll go back to the pathological things and the medicine. Okay. So thanks for watching. See you in the next video soon.